Now we want to talk about the topics about the area. So first let's look at the approximation to the area. So this is the example y equals f of x, which is x squared. So we want to get our aim is to get the exact area for this shaded region, yellow region, which is the region between the curve and the x-axis from 0 to 2 on the 0 to 2. Okay, so the idea is let's divide our interval from 0 to 2 into 4 subintervals. With equal length. We denoted the equal length with delta x. So for this one, we divide into 4 intervals. One interval is from 0 to 1/2. Another one is, this is the first one, this is the second one, right? This is the third one, this is the fourth one. For each interval, they have the same length, which is 1/2, right? So how to calculate the length, which is 2, this is the endpoint 2, minus the first endpoint 0, over, we have 4 intervals, so divided by 4. So this is the 1/2. So this is the length for each interval. On each interval, we form a rectangle, okay? So for this interval from 0 to 1/2, we form this rectangle. We use the height as which is the f values at the right endpoint for each interval. So right endpoint is 1 for the second interval. We use this as our height. We use this one as our height. We use this one as our height. Okay? Then we compute the area for each rectangle. Then add the map. So the area can be approximated by, for each rectangle is the base times the height. The base is here is 1/2, right? This is the length for each subinterval times the height. Height for this one is here. This is the f of 1/2, right? Plus 1/2 the second one, which is times f of 1, plus 1/2 times f of 3/2, plus 1/2 times f of 2. Okay, so this is the approximation if you plug in. So f of x equals x squared. So this is 1/2 times 1/2 squared, plus 1/2 times 1 squared, plus 1/2 times 3/2 squared, plus 1/2 times 2 squared. Then you add the map, this will give you a number, right? So this is we use the right end point as its height. So we call this sum to approximate the area. So we call this sum to be the left sum. Okay, so we can use another approximation. So if you have, so y equals x squared, so 2, we still divide into 4 subintervals with equal length. We use the left endpoint as our height. So here, this is the first rectangle, which is just a line. We use the left endpoint as height, left endpoint as its height, left endpoint as its height. So the area can be approximated by 1/2 times f of 0, right? This is the left endpoint. Plus 1/2 times f of 1/2, right? This is the second rectangle. We use the left endpoint. Plus 1/2 times 1, sorry. And plus the last rectangle, which is 1/2 times f of 3/2. Right? So this will give you another, if you plug in the numbers, this will give you another approximation. And for this approximation, we use the left endpoint for each interval as its height, right? Left endpoint as its height. So we give a name which is called the left sum. Sorry, I made a mistake here. In this one, we use the right endpoint. So this is we call this is the right sum. So actually, these are the two approximations. Actually, we can have more approximations. Okay. We have more approximations. We still divide into our interval into 4 subintervals. But for each one, we pick an arbitrary point in each interval. This is C1. We use this one, the f value at C1 as its height to form a rectangle. Okay, so here's C2. We use this one as its height to form a rectangle. And here is C3. And we use this as our height. F values at C3. And here is C4. This is the height. Right? So the area can be approximated by 1/2 times f of C1 plus 1/2 of times f of C2 plus 1/2 times f of C3 plus 1/2 times f of C4. And C1, C2, C3, C4 could be the left endpoint. This is called the left sum. C1, C2, C3 to be the right endpoint, the first one, which is called the right sum. Left endpoint is called the left sum. C1, C3, C2, C1, C2, C3, C4 if are the midpoint, which is called the mid sum. Okay, so but which one is better? We don't know. We don't know. We cannot identify which one is better. Okay, so if you want to get a better approximation, so the idea is we want to increase, we can increase the number of subintervals. Okay, so here our subintervals is 4. The number of subintervals is 4. If we increase to 100, then you can imagine you must have a better approximation. Right? If you have many subintervals, right, then you form rectangles on each interval. Right? Then you must have a better approximation. If the number of the subintervals approaches infinity, so you can imagine each subinterval is very tiny, right? It's almost a line. almost the line. So if you add these up, it would be the exact area. This would be the next topic about the finding the area by limit process.